in forward active mode for it to amplify. So today we'll see how one does this biasing when one is making amplifiers using BJT here. All right, so we'll come back to these questions. Some interesting questions related to this particular topic are: should one use more resistors or transistors in an amplifier circuit? Theory of evolution of circuits. Is there a best bias or a quiescent point? Okay, keep these things in mind, and then we'll see. All right. So I have a bipolar transistor. We all know that bipolar transistor can amplify, and I have a load resistance on one side, and I have a source which I want to amplify. The issue, of course, is that given a bipolar transistor, given a signal, and given a load, can I simply connect them up and hope that it would amplify? Will it amplify? Simply connect the source to the base here and connect the load to the collector here. Will this circuit amplify or not? Yes or no? No? Okay. We have seen graph like this. What is along the y-axis? Collector current, collector emitter voltage. We know that we need to bias it somewhere here, forward active mode. And in this particular circuit, where is the bipolar transistor biased? Where will it be biased? So this is a small signal voltage here. So forget about this. Where is it biased? It is biased here, right at this particular point. Why? It is biased here because I don't have any, independent of Vs, I don't have any voltage here. My transistor is in cutoff state. So it's over here. It's not saturation. It's not saturation. It is actually cutoff. The base current is 0. Collector current is 0. Okay. So my transistor is right now biased here. It's not going to amplify. Okay. So I need to take my transistor from here to somewhere over here. Right. So somewhere over here. And this is the forward active mode. And if I do that, and then on top of that, I apply my input voltage here, then I can hope for amplification. So the first thing that I need to do is take my transistor and put it in the forward active mode. And so this whole process of taking a transistor and putting it at a suitable point in the forward active mode is what we call as biasing here. So what we have to do is, before we apply our input here and connect a load here, what we need to do is we need to add additional circuit. We need to add something to the base side here, something to the emitter side here, something to the collector side here. And the purpose of all of this is to take my transistor and put it in the forward active mode. Okay, so these are all part of biasing circuits here. And once I do that, then if I apply an input voltage here, then the transistor now is in forward active mode. Now when I apply an input voltage here, this input voltage goes through my this part of the circuit and appears in an amplified form at the output here. So I have to take my transistor, add these additional things to my transistor here to put it in the forward active mode. That's the purpose. Okay. Now, when I do that, also keep that in mind, that what is happening is when I'm amplifying, I'm of course amplifying a voltage, but I'm also delivering power to the load. And what is happening is, as I've said, the signal power is very weak. So very little power actually flows from this signal to the load here. That's very weak. The power is coming from here. The power is coming from this supply and flowing into the load here. So input power is small. So when I try to bias my transistor in forward active mode, some of the things that I have to be careful about is, remember, what will happen is that depending on how you bias, you will get a particular amplification factor. I've shown you here this particular graph here, right? And said that I want to bias it here. If you bias it here, you'll get one kind of amplifier characteristics. If you bias it over here, you'll get different amplifier characteristics. Okay. So now, if you're interested in a certain amplifier characteristics, and you decide that this is the bias point that will give you those amplifier characteristics, now I have to make my bias point very stable. I don't want temperature to change it. I don't want temperature to change my bias point from here to here, because this bias point is what is going to give me the desired amplifier characteristics. Similarly, I'm not going to make only one amplifier. I'm going to make hundreds or thousands or millions of amplifiers. Different transistors have different beta. And therefore, even though my transistor may have different beta, I don't want my bias point to get affected. A transistor may have a beta of 100. Another transistor may have a beta of, let's say, 130. Another one may have 75. I want my bias point to remain at the same position. Because if the bias point gets affected, my amplifier characteristics get affected. Okay? So while biasing, we have to keep in mind that the bias point is stable against variations in temperature, current gain. It should not vary too much with the supply voltage. And it should be, my biasing arrangement should be such that it's an efficient biasing. In the sense that, remember, our goal is to take power from here and deliver it to the load. I don't want my power to be lost in the biasing circuit here and biasing circuit here. These are power which is lost. My interest is only in the power which is delivered to the load. So I don't want power losses here, and in these regions here. So while I'm designing my bias circuit, I have to keep these things in mind. Bias points, especially bias point, is stable against variations in temperature, current gain, and needs to be an efficient biasing here. All right. So the variations to watch out for are the following. One of the variations is the base emitter voltage changes with temperature, and approximate rule of thumb is for silicon bipolar transistors 2 millivolt per degree Celsius. Okay. So keep in mind that if you're going to operate from 0 degree to, let's say, some 80 degrees, so you're going to get 80 into 2, 160 millivolt change. And that 160 millivolt change in VBE should not cause a change in the bias point. Okay, so that's one change to keep in mind. The other one that I've said, that even if you take the same transistor manufactured by the same manufacturer and you measure beta, for example, you could go in the lab and collect some 100 transistors or 1,000 transistors and go ahead and measure the beta of all the transistors. And what you will find, the beta varies here. And typically you may see a histogram like this here. You will find most of them fall here. Maybe, let's say, the beta nominal value is supposed to be 100. Most of them will fall here. But some of them will have 140, 160, even some may 180. And some may be even as low as 60. So beta is going to vary. And now, despite this variation in beta, that's what I said, you're not going to make one amplifier. Your interest is in making thousands of amplifiers. And you cannot measure each transistor's beta and design it accordingly. You will have one design, and that design has to work for beta in this particular range. Okay, so which means my biasing circuit should be insensitive to beta, at least in this particular range here. If it varies linearly with beta, then when I have a beta of something, I will have a collector current of 1 milliamperes. When beta becomes 180, I'll get 1.8 milliamperes. So that's not going to work. Okay, so you have to make it insensitive to variations in beta here. So these are two things to keep in mind here. All right, there are two ways of biasing. This particular graph illustrates that, two ways of biasing. The left one shows a circuit which is built on a PCB, a printed circuit board, where the components are discrete. I have a discrete transistor, discrete resistors here that you see, and I'll have capacitors and all that. So two ways of building circuits. One is a discrete circuit where the components are integrated on an insulating substrate, a PCB. And the other one is where I integrate the whole thing on an IC, on a piece of silicon. Now, depending on how you are going to make the circuit, you will design biasing in different ways. If I'm going to make it for a PCB or a breadboard and all that you do in the lab, then what I'm going to do is that resistors and capacitors are cheap, transistors are relatively expensive, and therefore I'm going to design a biasing circuit which uses lots of these. A lot of resistors, capacitors and all that. Okay? So my biasing circuit will have emphasis here. I'll liberally use my resistors and capacitors. I can use a 10 microfarad capacitor, 50 microfarad capacitor. These are just available off the shelf, very cheap. While if I'm building it on an IC, none of those capacitors are available to me. I can't have any microfarad capacitor. I can't have any nanofarad capacitor. So I can't use any of them. Not only that, resistors are in general expensive. They take up a lot more area. You know, if I look at a particular silicon area, resistors will take up a lot more area than the transistors. Which means that when I design my biasing circuit or the whole amplifier, I would use lots of transistors, no capacitor, and as few resistors as possible. So you'll see two different classes of circuits then. A circuit design as for an IC, which we will call as an IC amplifier, or a circuit designed for a breadboard or a PCB, discrete amplifier. Okay, and depending on what your target is, you'll find that the circuits can be different. Okay. All right. This is a biasing circuit that you will see towards the end of today's or next lecture. This is a good biasing circuit, very popular. Biasing circuit, which part are the biasing circuits? All the ones in red that you see here. R1, R2, RE, RC, CE, CB, CC here. That's a good biasing circuit for discrete implementation. Okay. And now so the whole, all these components in red, their whole aim is to take the transistor, put it in forward active mode. Now you apply a signal from here. The signal goes through, gets amplified, and appears across the load. So now what I can do is, of course, tell you that this is a very good biasing circuit. I can take it up. I can analyze this particular circuit and tell you how to calculate the bias point. I can go that route. Or the other route is a different route here. You know, if I do that, what you will not realize that, you know, this particular circuit didn't come to a person's mind all of a sudden. If you think of a new circuit, new complicated circuit, it doesn't come to the mind of a designer all of a sudden in a complete form like this. Circuits also evolve. Circuits also evolve. And what I'm going to do is, you know, arrive at this particular solution that you see here through a gradual approach. I'm going to start from a very simple biasing like this here. Why go to this? You know, I can give you this, but you will not realize why go to this complicated solution. So we'll start with a very simple biasing. And once we start with the simplest biasing, we'll see there are problems in this particular approach. That this biasing will not be good. And how do we say whether it's good or bad? We'll compare it. Is it sensitive to temperature? Is it sensitive to beta? These are the two things that we'll see. Okay. So we'll find there are problems in it. And once you realize what the problems are, then you try to improve this particular circuit and you may get something like this. Right? So we'll see that. We'll go through this journey. Once you go through this, you'll see, well, this is better than this, but still has a problem. And you'll say, well, this is a better solution. And once you go here, now you're increasingly seeing that things are getting a little bit more complex. Then you'll find even this has a problem. Then you'll say, well, let me go here. And then let me go here. And then let me arrive here. Okay. So that is our approach. We'll start from here. Very simple approach. And then we'll gradually arrive at here. Now, while you start from this particular simple approach and you arrive here, what are you seeing? You are seeing that at every stage you are solving some problem. At every stage you have a problem which you are solving. You solve one problem and then you solve another and you another and another and another and then you arrive at this. Now you will realize what are the problems that this particular circuit really solves. Why was this circuit designed in this particular manner? Okay, so that's the goal here. So that's how we'll start. Okay, so let's start with the simplest one. This is the simplest biasing that you could think of. My goal is to put the transistor in forward active mode. Right? Forward active mode means what? I need to forward bias the base emitter junction. So I simply take a voltage and you want to forward bias in base emitter voltage. So you put some value here, 0.7 or 0.72 or whatever. Right? Why go as, why use resistors and more complicated solution? Just put a battery here. And then I want a particular value of collector voltage here. Okay. So I have a supply. Let's say I have a supply of 5 volt and I want a collector value of 2 volts here. So I have to put a resistor in between. I have to put a resistor in between to cause a drop from 5 volt to 2 volt here. The other thing is, note that I'm going to take an output at this particular point for an amplifier. If this point is directly connected to VCC, then this point is a fixed voltage. I can't get any output here. The voltage cannot vary. Okay, so I have to put a resistor here. Alright, so this is the simplest biasing that you can think of. Apply a voltage here and put a collector resistance here so as to arrive at this voltage here. Okay. Now, I have to apply a signal. So you apply a signal from here. Right, you attach a signal here and you attach a load through a capacitor now. Why are we putting a capacitor? Well, if I don't put a capacitor, as you can see, what will happen is that my, for example, let's say I want to put this at 2 volt. And therefore, I require a resistor of some 2K. Now, if I don't put a capacitor and I just connect a load and the load is 100 ohm, what will that do? I have 2K here and 100 here. It will upset my biasing. It will upset my biasing. So what I do is I use a capacitor to block the influence of my load on my biasing here. Okay, so that's the purpose of the capacitor here. All right, so let's look at how good or bad this biasing is. Now, here I use the expression IC equal to IS e to the exponent VB by VT. My collector current goes as exponentially with base emitter voltage here. So whatever voltage I apply, that is going to, depending on the voltage that I have, I can get a collector current, right? So remember, what is the goal of biasing? Biasing means it has to be in forward active mode and the transistor is conducting some amount of collector current, whatever collector current is of interest, and there is some voltage that I want here, collector emitter voltage. That's the purpose of biasing. A IC of certain magnitude and a VCE of a certain magnitude. Okay, so now this is telling me that I can do that. I can apply a base voltage here, and base voltage is equal to base emitter, and therefore I can get a collector current. The trouble, of course, is you realize that it's extremely sensitive. It's extremely sensitive. If I look at that any change in delta VBE, note here, delta IC is IS exponent VB by VT into delta VB by VT here. So what it says is delta IC by IC, I can look at a percentage change in collector current is delta VB by VB into VB by VT here. And what this is telling you is that, what is this quantity? Typical value of base emitter voltage would be what? Approximate 0.7. And this one here is 26 millivolt. So what is the ratio? 0.7 by 26 millivolt is how much? 700 millivolt divided by 26 millivolt. It's a large factor, right? It's a large factor here. So what this is telling you is a very small change in VB, a small change in VB. Let's say your VB, the bias voltage changes by 10%. The bias voltage changes by 10%. By how much will your collector current change? 10 multiplied by, maybe this is a factor of 20 or 30, changes by more than 100%. So it's extremely sensitive circuit. I don't want that. You know, a little bit of change in base voltage here is causing so much change in my collector current. So that's not very good. Remember, I want my biasing to be insensitive to changes in temperature, changes in beta, changes in the voltages also. And this is extremely sensitive to any change in the voltage here. Why? Because this is getting multiplied by VB by VT. The other thing that you note here is extremely sensitive to temperature, right here. I apply a constant voltage, let's say 0.7 at room temperature. Let's say I get a current of 1 milliampere. Let the current change here. Let the temperature change here. You see it's an exponential, and therefore my collector current changes drastically. So it's extremely sensitive to temperature. It's very sensitive to the base voltage that you apply here. You have to have very, very precise value of this voltage. Then only you'll get the current that you want. Any small change in the this voltage here, VB, is going to cause a lot of change in the collector current. Okay. So from that angle, then we realize that this circuit is not useful. It's extremely sensitive. Yes. Why? Temperature sensitive because you're applying a constant voltage VB, right? So this voltage is fixed. This voltage is fixed, and as you change the temperature, two things change. This thermal voltage changes, and this IS also changes here. Both of them rapidly change. Okay, IS is a function of exponential function of temperature. Okay, and that causes a change in this thing. But another way of looking upon it is, all of you know now that if I change temperature, by how much does my base emitter voltage change? 2 millivolt and all that. So it's the same thing here. What we are seeing is the collector current is very sensitive to base, and similarly the collector current will be very sensitive to temperature also, because temperature effectively changes the base emitter voltage here for a constant current. So the problem with this particular circuit is we are not happy with the sensitivity. Extremely sensitive, because this VB by VT is a large factor here. Any percentage change in VB causes a large change in collector current. So that's not a useful thing in the biasing here. So now the issue is, how do I make it insensitive? How do I make the collector current insensitive to VB. Reduce the sensitivity of collector current to the base voltage here. How do I do that? Well, I don't apply my base voltage directly here. Suppose I apply it through a resistor. Let's see whether that will help. So earlier I was applying the voltage directly to the base. Now I'm applying it through the resistor here. Okay. So let's do that. Now you see IB will be equal to VB here minus VBE by RB here, and IC will be equal to beta times IB. That's the relationship that I have. So let's look at it. Delta IC by IC here. Now again I'm calculating what is the sensitivity of IC to a change in, let's say, base voltage and base emitter voltage here. Okay, so delta IC by IC is minus delta VB, but you can easily differentiate and get this value here. Now you want this circuit to be insensitive to changes here. Delta VB, let's say, even if it changes, I don't want my collector current to change a lot. Similarly, base emitter voltage changes. Why? Because of temperature. As I increase temperature, effective base emitter voltage drops by 2 millivolt per degree Celsius here. So I don't want my IC to change despite changes in base voltage here and base emitter voltage here. What do I do? So for a 50-degree change, I will have a base emitter voltage change of 100 millivolts. So how do I reduce the sensitivity here? What do I do? This is fixed. Delta VB is fixed. Delta VB is, let's say, some fixed quantity here. And I want to change delta IC by IC. I want to make it small. The way to do it is make the denominator large. And how do you make the denominator large? Note that VB minus VBE. Make it large here. How large should I make? As I said, suppose my delta VBE due to temperature change is, temperature change is, let's say, 50 degrees. So 50 into 200 volt here. So if this is 100 millivolt, I must make VB minus VB much larger than 100 millivolt so that my delta IC by IC doesn't change here. So I need to make how much? At least, if this is 100, much larger means what? At least a factor of 10. When you say something is much larger than something else, at least we are talking about 1 order of magnitude. So you must make VB minus VB at least equal to 1 volt. Okay. So how do I make VB minus VB equal to 1 volt? Well, so this is telling you a constraint. How do you bias? Is telling you that if you want this particular circuit to be insensitive to changes in VBE and all that, you must make VB minus VBE, which is nothing but the drop here. This drop IB RB larger than 1 volt. So it is telling you how to bias this particular circuit. You must make this drop here, IB RB drop, larger than 1 volt. Now the larger that you make, the more insensitive the circuit is going to become. If you make it 2 volt, that's even better. 3 volt is even better. So you keep on increasing IB RB and the circuit will become more and more insensitive. Okay, more and more insensitive here. So that's the constraint that one gets on the design of this particular one. The drop here, IB RB drop, has to be larger than 1 volt, at least 1 volt. Okay, more, even better. Now, any problems with this particular circuit, or is this the best biasing I can get? All the problems solved, is it? Okay, why use a capacitor at the output? I've already said why, because you don't want biasing to be affected here, right? For example, this is telling you that I have a collector emitter voltage VCC minus ICRC. If I put a capacitor, if I didn't put a capacitor, note that VCC minus ICRC starts depending on RL, and I don't want that. I want my biasing to be independent of my load. Whether I put 1 kilo ohm load or 2 kilo ohm load or whatever, I don't want my biasing to be affected. Okay, so that's for that reason. We decouple the two. All right, we'll see in a minute what is the problem with this one. Let me take a quick example here. So I want a bias point of 1 milliampere and VCEQ. Q means quiescent point. Okay, bias point, quiescent point is, we keep on, sometimes we write IC, sometimes we write ICQ. So VCEQ equal to 2.5. That's what I mean by bias point. A particular value of collector current and a particular value of the collector emitter voltage. Now, we are asked that design this particular circuit. I think the design is already given. To give you 1 milliampere of current and VCQ equal to 2.5. So how do you do that? Well, we have these equations. IB equal to VB minus VB by RB, IC equal to beta times IB, and we know VCE is equal to VCC minus ICRC here. So we have these equations here. Now, while we have these equations, we keep in mind this constraint. I would like my IB RB drop to be larger than 1 volt here. Okay, so we keep that constraint in mind. If you don't have this constraint, then your design will not be a correct design, will not be a good design here. So from here, basically then, we know the value of IC, which is given here 1 milliampere. So we know the value of IB. And once we know the value of IB, we know that I have to keep IB RB greater than 1 volt. So I get a value of RB. Okay, so we get a value of RB from that constraint here, from here. And RC then we get simply once you know collector current and you know the voltage here, so you get a value of RC here. So it's straightforward. Given whatever bias point you are given, you can obtain what value of RB, what value of RC, and what value here VB is given to you. So why did we choose VB equal to 5 volt? Suppose you were given simply VB here, RB here, RC here, and 5 volt here, and you are asked to design the bias circuit. What value of VB will you choose? I've chosen 5. Why? Well, I already have a power supply of 5. Why will I choose some other power supply? If I choose some other power supply, then I'll have to get another power supply, right? Or if I don't choose another power supply, then I'll have to derive it from here using a more complicated solution. So for that reason, if this is 5, I've chosen here as simple 5 because it avoids complexity. Okay. Now in this particular circuit, so this is if you look at it, this is a viable circuit, but we'll see in a minute the problems with it. If you can look at the expression here, you will see that the circuit is very sensitive to. See, we have made it insensitive to temperature and other things by making IB RB larger than 1. What is it still very sensitive to? Beta. See, IB is fixed by VB minus VB by RB. And then IC simply beta times IB. If beta becomes larger, IC becomes larger. Beta becomes smaller, IC becomes smaller here. So it's extremely sensitive to beta here. So that's something which is a problem that still needs to be solved. But before we go to that, so we have a capacitor here that we use, and note that how do we choose a capacitor? Well, we should choose it in such a way that the frequency at which you are going to work, your signal frequency, for that signal frequency, the capacitor should be a short, should act almost like a short here. Because note that the signal is getting amplified, appears over here, and then has to go to the load. You don't want your signal to drop across the capacitor. Okay, so whatever is the frequency of your interest, if you are working with audio frequencies, and let's say the lowest frequency that you're interested in, let's say is 20 hertz or 50 hertz or so, you should make sure that at 50 hertz, the impedance of the capacitor, which is 1 by omega C, should be much smaller than the load value, whatever is the load, so that the capacitor to your signal appears to be transparent. Signal straight away goes to the RL here. Okay, so that of course translates into that your upper cutoff frequency or lower cutoff frequency should be below the range that you are interested in. That's what it will translate into. Okay. Now, besides the beta problem that you have, I'm trying to point out another problem that this particular circuit has. Okay. So this is the circuit that we are talking about with the biasing through VB, RB, and RC here, and we have an RL here and a VS here. Now, when we look at this circuit, let's calculate the voltage gain. What would happen to the voltage gain? So if voltage gain meaning V0 here divided by Vs here. So what we'll do is we'll write down a small signal circuit. Small signal means VCC will become ground, VB will become ground here. VB will become short, and this is the circuit that we will end up with. Everybody sees that? Why? Because a constant voltage source becomes, in small signal analysis, a short. Remember, although we draw like this, what it means is that I have at this node, I have a battery which is equal to VCC. One terminal of the battery is here, the other terminal is ground. And that's why this, when the voltage source becomes a short, this point becomes a ground here. This is of course ground. Capacitor, I've said, under small signal, at the frequency of interest, capacitor also acts as a short. So I have an RL here, I have an RC here, and I have an RB here. I can rewrite like this. Same thing, RC and RL here. Next, what will I do? Take my transistor out and put my hybrid pi model here. And let's not worry about high frequency at present. Let's say, look at a medium range frequency here. So instead of the transistor, I'm going to put an R pi, GM VBE, R naught here. So I'm going to take my transistor out and put this model here. So I get this here. Same circuit. The transistor has been taken out. This is my transistor here. RC and RL are there, of course, and we get this one here. Now, what will be the gain? The gain that I'm interested in is V0 by Vs. Okay, so let's calculate. The first thing that I will do is I'll calculate VBE, base emitter voltage, which is equal to R pi. There's a voltage divider here. R pi by R pi plus RB into Vs. That's VBE here. This VBE causes a current to flow here, GM VBE. And this current flows through what? A parallel combination of R0, RC and RL. Okay, R0, RC and RL. So I get V0 equal to GM VBE, this current source, multiplied by R0 parallel RC parallel RL. And therefore, the gain that I get is V0 by Vs will turn out to be R pi by R pi plus RB, GM R0 parallel RC parallel RL. That's the gain of my amplifier. V0 by Vs will be this quantity.
Sir?
Yes.
Sir, when we have considered the small low frequency model for this transistor, why aren't we considering the capacitance?
Which capacitance?
The capacitance next term.
So capacitance is there, right? Capacitance is there, and I said low frequency means what? Low frequency model. So this is the hybrid pi model, which is valid right from DC onwards to a frequencies where the internal capacitors start becoming important. So I have to take the internal capacitance only at very high frequencies. Okay, so this model is valid right from DC onwards. So this is the model that I've used and plugged it here. The question that you're asking is about this capacitor. This capacitor is there, and as I said, at the frequency of interest, it's a short. That's why we've removed it. You see, it's a short here. Capacitor, because short meaning its impedance is very small. So we have approximated it by a short here. So that's what we have done. Okay. So this is the gain that we get. AV equal to minus R pi by R pi plus RB, GM R0 parallel RC parallel R. Okay. Now note also, how is your amplifier really amplifying? Look at the steps here. What does your signal do? Signal causes a change in VBE. Any signal that you apply here, it causes a change in the base emitter voltage here. That change translates it into a current here, GM VBE here. So you're seeing, maybe if you want, 3 steps to amplification. 3 steps are there. One step, Vs causes a change in VBE. That's the step number 1. Second step, VBE causes a change here, current. GM VBE current starts flowing in response to this one. The third step, this current flows through a load resistor here, and you get a current, voltage here. Now, if you want a very high gain, what do you want? If you look at these 3 steps, what do you want? You want entire Vs to appear over here. You don't want it to be dropped across RB, because the signal that you apply, if it drops across RB, that signal is lost. That part of the signal is lost here. So you can see the loss here. There's a voltage divider here, R pi by R pi plus RB. There's a loss here. You want your entire signal to appear across the base emitter here. That's the first step. And of course, you want GM to be large so that you get a large current here. And then this current has to flow through this combination here. So you require RL is not under your control. RL depends on the load. So you want then, if RL, whatever value of RL, you want RC and R0 to be much larger than RL, so that this current here flows entirely through RL and develops a voltage here. So you're seeing what are the requirements for building a high gain. And the first major problem that you see in this particular circuit is what? This Vs is getting dropped here. And I'll just show you through some calculations the problem that is there here in this drop. Okay, so this is the amplifier that I have. This was the circuit example that we had taken. Let me calculate for ICQ equal to 1 milliamperes and VCQ so much. Let's calculate GM. GM is IC by VT. 38. R pi is what? Vt by IC multiplied by beta, 2.6 kilo ohm. R naught is early voltage divided by IC, which is 100K. This was my AV minus R pi by R pi plus RB and so on and so forth. If I go ahead and put my value of R pi and RB, this is what I get. Gain of 0.16. And so, I have biased it properly. My biasing is insensitive to temperature and VB, and I don't get any gain. And who's the culprit? Who's the culprit here? This factor note, GM R naught, this is fine, right? Look at the steps. As I said, steps in building up the gain. This is okay. 27.2 is okay. This is the problem here. R pi by R pi plus RB, this is 6 into 10 power minus 3. What is happening? Your signal, instead of appearing across the transistor, is the transistor which amplifies, right? The signal, instead of appearing across the transistor, most of the signal is dropping across RB, right? Look back here. This signal is not going to R pi. Very small fraction is going to R pi. All of it is dropping across RB. So the first problem that we identify, the first problem was the circuit is sensitive to beta. But even before that, the circuit now is not working as an amplifier. Circuit is not working as an amplifier, so what do we do? What do we do? We have to increase R pi. No, note that this bias point is fixed for some reason. How do you change R pi? You will have to change ICQ. So don't touch that. Let's say the bias point is fixed. And for that bias point now, what changes should I make to my circuit so that I start getting an amplified factor? Well, you can obviously see, why do I need this RB? I need RB to bias. Biasing is a DC, right? And this RB is appearing in my signal path. So what should happen is that my signal should not see an RB. My signal should not see RB, but RB has to be there for DC. So what do I do? Well, use a capacitor to bypass. Okay? So you can try that. So the problem, as I said, is a large fraction of input gets dropped across RB here. So what you are saying is I should put a capacitor here between this point and this point here, and then that allows my signal to bypass. Okay? There's another problem before we go to the solution. The problem is as follows here. I'm showing a biasing voltage VB here and a signal here. Okay? Many times what would happen is the signal that comes in, signal is an external signal, comes in such that one terminal of the signal is ground. And this voltage that you see here is also one terminal is ground. Okay, many times you will see that the bias voltage here for biasing, one signal is ground, and signal also one terminal is ground. How do I connect them in series? I mean, I can't connect them in series. So you could connect them in series only because I was thinking that both the terminals are floating. Floating means they're independently available to me. But if one of the terminal is ground, how do I connect it in series? If I do connect it in series, what will happen to Vs? If one terminal is ground, so this one will become ground here, so my Vs will get shorted. So many times I have this situation here. One terminal of the biasing voltage is ground, just like the biasing voltage that I said here. If VCC is something here, plus one terminal is ground, 5 volt, and the other terminal is ground. And similarly, this one, let's say whatever it is, one terminal is ground. Then I can't connect them in series like this here. It's not possible. Okay? These problems are avoided. So two things we are saying, that we want to bypass RB from the signal path. And the other one is I can't connect them in series like this also. Both these problems are solved through this means here. If you look at it, both of these problems are solved. I am not connecting them one on top of each other any longer, and my signal now doesn't see RB in my signal path. Both of them are avoided. Both problems solved. Agreed? Because now note your signal will travel straight to the base and will appear across base emitter. And biasing is being done through VB and RB here. And each one of them has terminals to the ground. Right? And so both of these issues have been solved by using another capacitor here. So biasing is done here, and I put a capacitor here. Why? Because then if I, so that biasing is not affected. My VB, RB goes and bias my transistor in forward active mode in the way that I want. While if I didn't put a capacitor, what would happen? How much is this voltage? Input voltage that I want to amplify is very small, 1 millivolt, 2 millivolt or something like that. So if I don't put a capacitor here, what is the voltage? This is the voltage source. So what will happen to the voltage here? 1 millivolt, 2 millivolt, which means what? Base emitter junction is not biased at all. I need at least 0.6 or 0.7 volt to bias it, which means my transistor is in cutoff. It will not work. So to bias it, I have to put a capacitor here, which prevents the biasing to be, disrupted by this particular source. So it acts as a DC block, prevents any, this part here from affecting this voltage here. Okay. DC part of the voltage here. Sinusoidal part, of course, can travel through this particular one. Okay. Yes. Let's look at this here. Small signal model. Let's build a small signal model here. Let's see if this is correct. Again, I will choose the capacitor in such a way that at the frequency of interest, this capacitor's impedance is very, very small. So we have a short here. So I have VS, a short. I have RB. This battery becomes a short here. Then I've replaced the transistor by hybrid pi model here. And then I have RC here and RL here. Can you see now the signal, where does it go? VS? Straight to VB. Nothing gets dropped across RB. Straight to VB here. And then this builds up the gain, GMVB, and it flows here. And the gain now, AV is minus GM, R0 parallel, RC parallel, RL. R0 is very large, so it's minus GM, RC parallel, RL. And for the amplifier of interest, I'll get a voltage gain. I'll get a gain of 27 or so. So this is how we avoid the signal going through an RB. I don't want my signal to go through RB. And also the fact that one terminal of my battery here is ground, one terminal of the source also is ground. And therefore I can bias it also, and I can get the signal going into my circuit also. So both these problems are avoided by going into this particular means here. Okay. So realize why we put a capacitor and why we put a source here. If this voltage source was a floating source, then I could have simply connected them in series. That was possible. As we said earlier, what we could have done is simply maybe bypass RB here. We could have done that. Okay, simply bypass RB, and then that solution would have worked. But because I have this additional problem, I want to make it more general that one terminal can be ground, another terminal can be ground here, and therefore this is the viable solution now. Okay, and this gives me the gain that I require here. Okay, let me stop here.